All right, and all my recordings should now be correct every time I do this throughout the semester. And why is that? There it is. Come on now. There we go. Okay, so the last time we went ahead and left off, we were talking about rules for how we denote how accurate a number is, or what sort of precision it has. Okay? So you may have noticed that whenever you use your calculator, you oftentimes have numbers that come out and they are just incredibly long, right? And sometimes you could have numbers that are 20 decimals long, right? Did that number suddenly get more accurate, more precise because you used the calculator on it? Uh-huh.
Can you tell me again which calculator to get?
So it really, you don't have to get an exact calculator. So any scientific calculator that doesn't have an internet connection, that's fine. Okay. Personally, I really like the TI-83 Plus. It's just a very easy to use calculator, and it's the sort of last calculator they made that doesn't have an internet connection.
The TI-84 Plus has internet?
It has, one of the TI-84s does not have internet. The only reason I don't recommend that one is that it takes a lot more charge and has a lithium-ion battery.
Okay.
So it's a lot more expensive. It also doesn't last as long. Okay. TI-83 Plus, I've been using one for 30 years. Still have it. Still works great. Yeah. TI-83 Plus, if you go onto the online auction sites, you can usually get it for about $10. Yeah. So. Okay. And so when we're looking at these numbers from our calculator, these numbers from our calculator did not suddenly become more accurate because they went up to 20 decimal places, right? They didn't suddenly gain that level of accuracy. They've just done math, right? If I divide 1 by 3, I get 0.3 repeating, don't I? And so that has infinite number of decimal places, doesn't it? It didn't become more accurate. Nothing about it really changed, did it? At least not physically. And so what you have to remember is you're oftentimes going to have to go ahead and round numbers. Now, the rules for rounding numbers is that if it's below 0.5, you round what? Down. Yeah. If it's above 0.5, what do? Round up. Okay. 0.5, what do? This is probably where you've been taught wrong, by the way. You round up. Yeah, that's the most common rule that people tend to follow. 0.5 is actually not the center. 0.5 is actually half of the center, right? It's between 0.5 and 0.6 that the center between 0 and 10 is. Okay? And so when you round up every 0.5, you actually make the numbers too large if you do a lot of calculations. Did I tell you guys about the Superman virus? No? Okay, so a virus created, it's famous from the movie Superman 2, because that's one of the first places it showed up in media. But it actually was based on a hacker group that did this to bank chain, and this has been done 3 times that we know of. Okay? The last time it was done, it stole over $400 million. So what it is the virus that you infect a bank, and every time they calculate, it rounds down on the 5th or 6th decimal place, and it just puts that money into an account. On every calculation, all the interest calculations, whenever you go for your interest on your loan, it does that. Okay? Now the bank already actually does this. Did you know that? Guess which way they round? They round in their favor. And so they're stealing like a hundredth of a penny from you every month. Okay? Now, if you steal a hundredth of a penny 100 times from 1 million people or 100 million people, that's a lot of money, isn't it? Yeah. And so, same sort of thing here. If you do this over and over and over off of large numbers data sets, if you round up every time you get 0.5, you will actually increase your number. Okay? And it will meaningfully do that. You can also do that. There was actually a head of the foundry that did that for the pennies. They stole little fractions of pennies that they knew that they could get away with due to the measurement, and stole about $10 million at the time. Anyways, so when you do this, the actual rule. Now, I'm not going to hold you guys to this. All my questions are going to be multiple choice. None of them are going to be so close that you're going to end up having to use this. But the actual rule for rounding at 0.5 is that if the number before it is even, you round up. If the number before it is odd, you round down. Okay? So basically, you round up and down at 0.5 half the time. And that evens that number disparity out. Okay? Most of you, that probably won't matter, though. So, but if you ever end up having to do the calculations in the data sheets for trials, like drug trials or something, or you do the accounting for a very large firm, keep in mind that this is actually very important. Okay, it very much adds. All right, so when we're talking about significant figures and calculations, everybody remembers the significant figures. We did the zeros and if they're significant or not. Okay. Now, when we're doing significant figures for calculations, if it's an addition, subtraction, the answer should match the least number of decimal places in the measured numbers. So whatever has the least number of decimal places, that's what everything goes towards. Okay? And this is because, think of it as a bank account, because money is what you guys are most used to dealing with large numbers on, right? So if we think of it as a bank account, let's say I have $10,000 in my bank account and my number is going to change by 1 penny. Is that going to have much of an effect? No, I really don't care that much, right? And so I'm not going to round my entire account to be like, I had a $10,000, I gained a penny, now I'm $11,000. That's not going to happen, is it? No. Or I lost a penny, oh, now I'm down to 10,000 from 9,000, right? Oh, now I'm 9,000. I don't round like that, do I? I don't discuss it like that. And so the same thing happens whenever you have addition, subtraction, whenever you have small or numbers in those. They just don't meaningfully change the number, do they? Okay, so multiplication, division. What if I multiplied my account by 1%? Would I be happy or sad? I'd be really sad, wouldn't I? If I multiplied my account by 1%, I'd lose 99% of it, wouldn't I? And I would very much notice, right? So if I multiply or divide by small numbers, I very much will notice. If I was to divide my bank account by 0.01, it'd go really high, right? Ooh, that's nice. If I was to multiply by 0.01, I'd be in real trouble, right? Okay, and that's why the stock market is so good, because it's multiplication. Okay, or so bad, by the way, because it's multiplication and division. All right, so large and small numbers make a lot of difference when I'm talking about multiplication, division. When I do significant figures with those, what I need to do is take the number of sig figs, and my answer is going to be that same number of significant figures, okay? Not cut it off at decimal places. Okay, so again, these are the rules for rounding. Whenever you're doing multiple step calculations, you should just go ahead and keep a few extra significant figures, or keep the entire number in the calculator and just keep using the entire number, okay? Never ever round until the very, very end. Right? Can anybody tell me why you'd not want to round until the very, very end?
So you can change your answer?
Yeah, it's going to significantly change your answer. Okay? It'd be like you rounding off every time you do a calculation in your bank. Technically, if they did that, you would actually never accrue any interest, because the amount of interest you accrue in a savings account is actually minuscule compared to the whole number, right? So if they just rounded that off every time they did it, you would never get anything from a savings account, would you? Yeah. So, Scientific notation. You've all probably seen this in some way, but this is scientific notation. What we're going to do is we're going to take the numbers that's greater than 1 through 10, and we're going to put that in a 10 to the power of, so that we can shorten how these numbers are written out. This also makes it far, far, far easier to deal with significant figures. Because if you do that, then everything that's shown right here always ends up being a significant figure. Okay? So this is going to be coefficient. Everybody's okay with that terminology, coefficient? It's what you multiply the number by, or the variable by. Okay. And so this coefficient is going to be a number that's greater than 1, less than 10, because if you have anything greater than 10, less than 1, then it would actually make more sense to put it over here, which is the 10 to the power of. Okay. And so a positive exponent is going to mean that the number is actually greater than 1. That it's actually, if you have a 10 to the first, does anybody know what that would be? 10, yeah. And so it'd just be 1.1 times 10 to the first would be 11, 110. Yeah. And so if we have 10 to the sixth, what would we normally call that? It's a million. 10 to the ninth, a billion. Yep. And 10 to the third, 1,000. Yeah. Okay, so if the number up here in the exponent is negative, that's the decimal places it's going to be. Okay, 10 to the negative 1 is a single decimal place, isn't it? Yeah. So for example, 1 times 10 to the negative 1 would be 0.1. Another way of thinking about these numbers up here that are in the exponents is if it's a positive number, then that's going to mean it's in the numerator. You're multiplying those. Okay? If it's a negative number in here, you could actually flip it upside down. You could rewrite it like so. So 1 over 10 to the n. Okay? That would be the same thing as 10 to the negative n. By the way, let me write over down here. Anybody ever seen that? Is that true? Yeah, it's true, isn't it? So 1 over 10 is the same thing as 10 to the negative 1. That's the exact same thing as what? 0.1. Those are all the exact same number. Okay? Yeah. Now, so the neat thing about these, again, is the coefficient right here shows you the exact number of sig figs. Whenever you write scientific notations, you only put the sig figs in there. So this would be different scientific notations and what they mean. And what you can see here is it's just a re-representation of the same sort of thing I've been talking about. By the way, any number to the 0th power is what? 1. Yeah. So any number to the 0th power automatically goes to 1. Okay? All right. So, for example, if we have 10 to the second, what does that mean? That means it's 10 times 10, right? Or another way of representing that would be 100. Those are all the exact same numbers. Okay? They mean the exact same thing. Okay. Percentages. It is a part divided by the whole times 100 to get into percent. Another way of saying percentage would be saying parts per 100. Anybody ever heard of parts per million, parts per billion? Usually like drinking water or CO2. You've heard it in the news. This would be parts per 100. Okay. And so what we take is, for example, if we have a whole population of the class, that would be the number of people in the class, right? And then this would be the number of people that have that trait we're looking for. People that write in books versus computers. Okay? Another way of saying this is percentages is also how your grades work, right? Okay, and so when we take an exam, if there's 40 possible points and you got 30 points, 30 would be on top, divided by 40, and then you'd multiply it by 100%, right? Okay. Anybody know what that would be? You got, yeah, 3/4 or 75%, right? Okay, and so again, we can convert fractions and percentages. If you ever start off with a percentage and you can assume numbers, an easy way to deal with percentages is just assume that your whole amount of anything is 100, right? That way you work in nice even numbers. Okay. Mass. Anything that takes up space can also be placed on a scale and weighed as mass. Mass is going to be a measure of the amount of material in an object. You will notice that this is a bit of a circular definition. It's actually very hard to define mass within this universe and anything that makes sense. Okay? And that's because everything we do has been related to mass all the time, right? Like you're automatically thinking mass all the time. You just don't realize it. Okay? Another way of considering mass is resistance to change in spatial dimensions. The reason you can't shift the Earth when you walk on it is because the Earth just weighs far more than you, right? It has a much larger mass. Okay? All right. Anybody know the difference between mass and weight? So, weight is actually the force of the gravity of Earth pulling on that mass. Okay? It is proportional if everything's the same distance from the planet. It is proportional to mass. Okay? Because the gravity constant doesn't change much. But if you were to take an object up to space, if you were to take an object up to the moon, what do you notice about their weights? You seen the astronauts playing up there? What happens to their weights? Yeah, they go down a lot, right? Yeah. Their mass has not changed. Same reason that the astronaut can't like shove the space station by just bumping into it. The space station still has a larger mass. Okay? But the weight goes down tremendously, and so they can like jump and never stop. Yeah. And actually, that's a real problem in space, because if you get detached from the space station, you can drift off forever. And that's actually happened a few times. They thought it might have happened recently with a shuttle. We almost lost the damn thing. Whoops. But anyways, if you go to Mars, for example, your weight will change. If you were to go to Jupiter, your weight would go up by about 100 times. You'd be crushed under your own weight. Smush. If you were to go to the sun, your weight would go up something like over 10,000 times. And it just, even if you got close to the sun, you just, right in. Okay. It is an acceleration, by the way, in case you're curious. It's a force accelerating you evenly across all your cells. So it's quite interesting. Volume. Volume is a three-dimensional measure of the space occupied by matter. We quite routinely use this in labs. We typically measure these using things like graduated cylinders. If you're in medical, they typically use a syringe, or they'll use a flow meter. Anybody know what a flow meter is? No? Anybody ever seen the IV bags and it has a little computer under it? And they can like dial in how much they want to give you? That's a flow meter. Okay? Yeah. It measures how much they're giving you in volume. All right. This is how we typically measure these around the house. Measuring spoons, measuring cups. We don't do that in lab because they're incredibly inaccurate. For example, we have these things called beakers in labs. If you use a beaker, your measures are going to be about 40% off. Okay? Really, really bad measurements, right? Okay. If you use a graduated cylinder, they're usually pretty accurate, actually. Within like 3-4% usually. Okay? Pretty good. Smaller graduated cylinders do better, but can't deliver as much, right? Okay. Typically going to be measured in liters or milliliters. Milliliters is probably the one most of you are going to see the most of. Okay? Does anybody ever heard of, give me 10 cc's? Yeah? No? Okay. So very common medical scene you see, very accurate actually. You give cc's very often in a medical setting. What they're actually talking about is that is cubic centimeters. Another way of representing cc's would be cm cubed to the third power, right? Centimeters cubed. That is the exact same measurement as milliliters, actually. It's just another name for milliliter. Okay? Okay. By the way, 5 milliliters is a teaspoon if you ever need that. So if you have a measurement in teaspoon, 5 milliliters would be the equivalent. I'm going to be honest. I typically end up having to go like tablespoon to milliliters quite often. And I end up having to ask Alexa all the time. Hopefully nobody played that around her. Or my phone. Okay, Google. I forget that one all the time. When you're in lab, by the way, we'll use mass quite often to measure things. This is a very, very accurate measurement you can do because we have digital balances. And a fun little fact, you can actually get very cheap digital balances that are actually incredibly accurate. They've gotten just ridiculously cheap. Yeah. So you can have, like, for $10 about the same accuracy of a balance that we have in the lab. It can only measure a small amount, though. Yeah. Ours can measure larger weights. But there's always a cutoff for every balance because of how a balance works. It has a little rod that actually moves over. If you put too much weight on it, it can no longer measure. And it'll lock the rod. Okay? If you put enough weight on it, it'll just break it. Because a lot of plastic pieces in there and fine metal pieces. Keep in mind, if you ever measure something's mass, heat does make a difference. Okay? So be very careful not to put something very hot on a balance. Density. Anybody ever heard of density before? Okay. Have you ever heard you're dense? Hopefully not. That's not a compliment. Though I find it funny that you'd think the opposite would be a compliment, right? You have low density. And yet it is not. It most definitely is not. Okay, so density is represented by a small d. This is actually a comparison or ratio measurement. And so what it is it's the mass of a substance divided by its volume. Okay? And so small d equals small m, which is mass, divided by big V, which is the volume. Typically, the units for this is grams per milliliter. Okay? The density of water, which is probably the most important density, and you should actually know that one, is actually, so typically it's going to be given as 1.00 grams per milliliter, okay? It changes depending on the temperature, but essentially it's always 0.999999, and then number changes, okay? So for your purposes, you're never going to probably need it anything as other than 1.00, okay? Grams per milliliter. Okay, does anybody know why things float in water? Why does a helium balloon float, a balloon you blow up with the air in your lungs, not float?
Has less density.
You got it. You got it. If something has less density than the substance around it, for example, this right here has less density than the water, it's going to float. If it has more density than water, then like that chunk of metal, it's going to sink. Okay? And so a helium balloon has less density than the air around it, and so it floats. A hot balloon can have less density than the air around it, and so that floats. When it cools down, it has more density and it sinks, right? Okay. The air blown from your lungs has a larger density for that balloon because the balloon skin adds weight to it. And so that ends up sinking, doesn't it? Okay. You know those cool little balloon things with the decorations where it like bobs along and it stays at a pretty consistent height without you messing with it? Can anybody guess how that works? You take a balloon that would normally float and just go off, and then you add weight to it until it just is in equilibrium. It's basically the same density as the air around it. And so it just stays in position. Yeah. Okay. All right. Anybody have any questions about density? Did anybody want to ask me about boats? How boats work? No? Okay. Okay. All right. Specific gravity is actually the specific terminology that you would use for a thing, whether something floats or sinks in liquid. So specific gravity is going to be a liquid density, is going to be measured with respect to water. Remember, water has a density of 1.00. That's at 4 degrees Celsius, actually, is where it's 1.00. And so that's close to the value at the body temperature. There's very little difference in that number for going up to body temperature, which is usually a little bit under 30. The ratio of the density of a sample to the density of water is going to be called specific gravity. It's noted by that abbreviation, SPGR. And so it's just going to be the density of whatever sample you have divided by the density of water. If that is greater than 1, that sinks. If that's less than 1, it floats. Now, the reason this is done is because the density of water changes a little bit depending on the temperature, and it can change from things like salt being added. Okay? That's why you float a little bit better if you ever try to float out in the ocean. Right? Whereas if you go to a pool of tap water, city water, you sink a little easier, right? Okay. It's a little harder to float. Okay, so again, this is actually a ratio of two densities against each other, and so the units actually cancel for this number. So you end up with this unitless number, and this number ends up being true for all the different temperatures because things change. The temperature of the water changes that density, and so you can get a sliding scale there. The specific gravity of a liquid, this can be measured with a simple instrument. It's called a refractometer. Let's talk about temperature now. We measure the temperature of a substance. It determines the hotness or coldness. It's often done using a thermometer or electronic temperature probe. In the United States, we use a Fahrenheit scale. Essentially, the rest of the world, with I believe one other exception, uses Celsius. So, yeah. Scientists actually use a different scale. This is an absolute scale. This is called the Kelvin scale. Anybody notice that our temperatures are degrees Fahrenheit, degrees Celsius? No? It has that little degree symbol? A little circle above it, right? Okay. Anybody know why it's a degree? It means it has an arbitrary start point. So like a circle, where do you start on a circle? Is there an origin for a circle? No. They're all the same, right? So you arbitrarily set a start point, and then you have degrees off it, right? The temperature scales, Fahrenheit and Celsius, have arbitrary start points. And so they are a degree symbol. Kelvin is an absolute start point. There's an absolute 0 for Kelvin. And so that one does not have a degree symbol. Okay? All right. The Kelvin is the SI unit for temperature, and that's specifically because it has an absolute start point. This is actually how they compare to each other. And so what you'll see is Celsius is actually kind of the easiest to use in everyday life, and that's because it has a 0 degrees Celsius, which is freezing point of water. Okay? And then the boiling point of water is 100 degrees Celsius. And so there you go. 0 and 100 degrees Celsius, very easy to set, right? Get some ice if you want 0. Get some boiling water if you want 100, okay? There you go. Kelvin is 273 Kelvin is equal to 0 degrees Celsius. So if you ever want to convert from Kelvin to degrees Celsius, what you do is you subtract 273 from it, right? And it has the same relative changes. Notice that 273 to 373 Kelvin is a 100 degree difference, right? It's that same sort of difference. Each degree Celsius is the same as a change of 1 Kelvin. Okay? Nice and convenient. This is actually the normal body temperature. It's 37 degrees. That would be a normal body temperature. Normal room temperatures are in the 20-something degrees, like 25-ish to 30 degrees Celsius. 30 would be on the warm side. Okay. This right here is then going to be Fahrenheit. It's 32 degrees Fahrenheit. Notice when it tells you to be careful about driving is what? A little bit above 32 degrees Fahrenheit, right? Yeah. And that's because that's when ice could start showing up. Cooking, typically you want to keep something hot at around 212 degrees Fahrenheit. Anybody know why that is? So that's the boiling point of water. It makes it a little bit difficult if you're just under that for the water to escape too fast. But it also makes it very difficult for anything to grow in it because things die at that high of a temperature. Okay? Really, usually anything above 200 degrees Fahrenheit, it's going to be safe to eat. Okay? Because things die. This right here is the body temperature, 98.6 degrees Fahrenheit. And so that is your temperature scale. This right here is the conversions between them. This is Kelvin to Celsius. So if you have a number in Celsius, like 0 degrees Celsius, you would add 273 to it. It's actually 273.15, in case you're curious. And that's going to give you Kelvin. If you have Fahrenheit to Celsius, these are the conversions right here. If you're going from Celsius to Fahrenheit, you have to take the Celsius number, multiply it by 1.8, and then add 32 to it. The order of operations absolutely does matter. Okay, so be very careful there. It's very common for people to mix those up and then get wrong numbers. Okay. By the way, I actually remember this as 180 divided by 10. And 180 divided by 10, because these differences match up. See 180 and 100. Okay? And that's why you get that ratio right there. 1.8 versus 1. It's 180 divided by 100, right? Yeah. So I remember the thermometers easier. In case anybody else is like me, there you go. So if we go from Fahrenheit to Celsius, Fahrenheit is going to be minus 32. And then you're going to divide it by 1.8. Okay? If you remember the calculation, the formula here, you can actually solve for one versus the other. That's all that is me just solving that formula. Okay? Anybody have any questions about that so far? All right. All right, so again, the normal body temperature, 98.6, 37 degrees Celsius. Now, your body temperature does vary from person to person. It changes throughout the day, depending on your condition, whether you're excited, aggravated, depressed, with emotions to some degree, though not reliably. That's why mood rings don't work. And so it changes throughout your day, throughout day to day, but not by a huge amount. Okay? If the human body temperature rises above 40 degrees Celsius, that's 104 degrees Fahrenheit. This is actually hyperthermia. What does hyper mean, by the way? High, yeah, greater than, right? Yeah. So thermia, your temperature, or your thermal equilibrium. Hyper, above. Okay. And so this will be hypothermia. This condition, after 104 degrees Fahrenheit and above, can cause convulsions, coma, or permanent brain damage. So you do not want somebody to stay at 104 degree Fahrenheit or above. That is 40 degrees Celsius, excuse me. By the way, what if they're 102 degrees and they're sick? Is that a problem? Do you want to stop that fever? Anybody know why your body gets hot when you're sick? Exactly. Yeah. So when you raise the temperature, it impacts the metabolism of the organisms within that temperature, and it makes it harder to reproduce. That allows your body to fight the infection more successfully. Okay? Though if you stay at 104 degrees Fahrenheit or above for extended periods of time, that's going to be very bad. Okay? Because then it's also fighting your own body is fighting itself and causing it to no longer be able to function properly. Okay? All right, so if your body temperature drops below 35 degrees Celsius, which is 95 degrees Fahrenheit, this is going to be hypothermia. Excuse me, that's a typo. It's not the same thing. Hypo meaning below, right? Yeah. All right, and so you're going to be feeling cold. Interestingly enough, you can actually not end up feeling cold from this. And the same thing with hyperthermia as well. The way your body works, actually, is not necessarily reliable to sense your own temperature. Okay? Oftentimes, you will not sense hypothermia. In this condition, you'll feel shakes usually. You'll have irregular heartbeat. You'll have slow breathing. You're going to be going into a dormant state. If it gets bad enough, you're actually going to start dying, right? And experience irreversible changes. Though that's not usually anything close to 35 degrees Celsius. You need to get a lot lower to really be harmed by it. Given enough time, you can die from 35 degrees Celsius. But it's going to take a while. Okay? They very successfully in hospitals hold people at hypothermia conditions to slow down things for like surgeries. They can slow things down so they can take a little bit longer. Energy. So energy is the capacity to do work or supply heat. Stored energy is going to be called potential energy. It's not being used yet. Can anybody identify some potential energy in the room? How about the batteries in your phones and devices? It's potential energy, isn't it? Okay. Or the fat that you're storing in your body. That's also potential energy. Okay. Kinetic energy. This is the energy of motion. Can anybody identify some kinetic energy in the room? Got it. You guys shifting, moving, writing, breathing, all those actions, right? Okay. So again, energy takes various forms. It's never created or destroyed, though. It just changes form from one form to another. This is the law of conservation of energy. Does anybody know the difference between a law and a theory?
A law is proven, while a theory can be debated.
Yeah. So a theory has oftentimes never can be proven. In science, things typically cannot be proven. And if you start going into logistics and the philosophy of logic, you find out that it's actually kind of impossible to ever prove anything. The best you can do is disprove things. Okay? And so when we're talking about a theory is something that you've tried to disprove, but you haven't been able to disprove. A law is something that's going to be just consistently tested every second of your life. Okay? So for example, the law of conservation of energy is being tested every single moment we're existing, right? Because we don't pop out of existence all of a sudden. Law of gravity tested every single moment of our life. If law of gravity fails, whoosh, we eject off the planet. Okay? And so, yeah. Laws are tested every moment. Theories are something you have to actually test and set up to test. Right? And so you can never be absolutely sure because you just can't run the number of tests that would be possible to actually make it sure. Right? Okay, so the SI unit for energy is going to be the joule. That's a capital J when you abbreviate it. You may have heard of the calorie before. There's a little bit of confusion there, okay? So be careful with it. So let's approach it with the actual calorie first. That's small c. Everybody see that small c portion? Okay, small c calorie. This is the amount of energy that's required to raise the temperature of 1 gram of water by 1 degree Celsius. 1 small c calorie would equal 4.184 of the joules that we just discussed. Now, this is very different than the nutritional calorie. That is the large C calorie that you've probably seen before. And so the large C calorie, abbreviated capital CAL, this is actually a kilocalorie. It's 1,000 times a small c calorie. Okay? And so 1 large C calorie is 1,000 small c calories. So when you look at the back of a package, that's actually in kilocalories. Okay? Okay. Heat. So heat and specific heat. Heat is going to be the kinetic energy that's flowing from a warmer body to a cold one. The heat is actually a form of energy. It is a form of kinetic energy. And really what it is that if I have one object and I'm like throwing it around and it's being shot out of things, I can calculate the kinetic energy of that fairly easily, right? What if I start taking those objects and instead of one object, I now have a million, billion, trillion of those? Am I going to be able to calculate the kinetic energies and which direction they're going? And yeah. If I have two objects and they're facing towards each other with equal kinetic energy, what would the overall kinetic energy be? It'd be 0. So what ends up happening is once you get very complex randomized systems, you can't really calculate the kinetic energy anymore. It just becomes too hard to do. Okay? So systems like, say, the air around us right now, which has trillions times trillions times trillions of molecules in it, right? We can't calculate the kinetic energy for that. So what we do is we have a measurement we call heat, and it's randomized kinetic energy. Okay? Where you have a bunch of different kinetic energies in different directions, different amounts of kinetic energy for different particles. Right? So just a lot of randomized kinetic energy. That's heat. Now, every substance has the ability to absorb or lose heat at the temperature as temperature changes. That's actually what you're thinking of when you think of heat. The specific heat capacity or specific heat of a substance. This is going to be the amount of heat that's needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. This is what you're thinking of as how fast things heat. Okay? Anybody ever notice that I'm boiling water in a pan? My pan gets really hot. My water doesn't get hot yet, does it? Anybody ever notice that? And the water's not boiling. I'm thinking it's not hot yet. I touch the pan, and what happens to my hand? I burn, right? And that's because the specific heat of a pan is very low. It heats up real fast. Okay? The specific heat of water is much, much higher than the metal. Okay? And so that heats up very slow in comparison. Anybody ever notice that when you see the weather forecast for like the Midwest and to some degree this western-ish Tennessee area, the parts without a lot of water bodies, that those temperatures range into like these really ridiculous numbers? Like it gets colder than this Siberia. It's warmer than Sahara sometimes. Okay, and then you go to like California and the coast, right? And the temperature is like this minuscule range that doesn't change much, right? Always kind of nice temperatures. Okay. The reason for that is water bodies. Water bodies suck up a lot of heat when you heat or cool them. Okay? And that's because they have a fairly high specific heat. Right? Anybody know what the leading use of energy residentially typically is? Yeah, heating and cooling. That's the largest use of energy, period, in any country. Yeah. Is heating and cooling various different things. Even in industry, they have to heat and cool water, right? Or heat and cool a substance like metal. Yeah. Okay, and so this right here is the specific heat again. It typically is abbreviated SH in most of the sources you're going to see. It is the heat over the grams times the change in temperature. So how much that temperature changes for the amount of substance you have with that amount of heat added to it. Okay. The metals are going to have low specific heat values because they heat up very quickly. The water will have a pretty high specific heat. There are things that have higher specific heats than water, of course. And you're going to think of those things as the things that, don't allow you to warm or cool very quick, right? So if you have like a really nice weather jacket, winter jacket, that would have a very high specific heat, right? Doesn't warm or cool very easily. So right here, this is the specific heats of various different substances. This one's in calories. Calories is actually the easiest one to remember because the definition of a small c calorie is the specific heat of water. So 1 calorie, the energy, divided by gram degrees Celsius. because it takes 1 calorie to warm 1 gram of water 1 degree Celsius. So that's actually the definition. They played a nice little trick there whenever they set up calories. It's kind of a shame they never got adopted as the standard, but that's okay. These are some different substances. You can see there's water right there. There's the human body. I know, right? We have a lower specific heat than water, don't we? Dang it. All right. And here's some other substances. Does anybody have any questions? Okay. So let's talk about the states of matter. You all probably know the states of matter pretty well. What's the states of matter? Solid, liquid. We got another one? Gas. Anybody want to try for some of the others? No? Come on.
Plasma.
Yep, plasma is one. You got, or supercritical liquids are also another state of matter. There's actually a couple other ones that are very esoteric, weird stuff. But realistically speaking, the only ones you're going to encounter in your daily life are going to be liquid, gas, solid. And then you do encounter plasma, but hopefully never close. Can anybody tell me where you've encountered plasma before?
Is it in your blood?
It is not. So that's just a mixture of these phases. It's kind of a weird use of the word plasma. It's a timing thing. The definitions weren't set, and then people use that. So it ends up being a bit confusing. But so the only plasma you've probably ever experienced in your life is lightning, actually. So that flickering flashes that happen, that you trail, that you can see for lightning, that's plasma. Okay? And so lightning generates plasma in the atmosphere, or one of those little lightning balls also that you can have in your room. Yeah. Those also can generate plasma. Okay, this is what solid, liquid, and gas look like. The gas you're not seeing right now. You're not experiencing it around you right now. Can everybody go like this so you can experience it? There you go, some gas. Or you can go gas again, right? Good. Please don't do the other forms of gas you can do right now. We'll keep those for later when you have privacy. Okay, so liquid. You're all familiar with liquid water, right? Okay, fantastic. What you'll notice about these is gas is basically particles going real fast, bouncing around all over the place, and not having any time to really interact or do anything. Okay? Liquid is when those particles are going a bit slower, but bouncing around fast enough that they can't just sit there holding on to each other. Okay? And usually you're talking about breaking about 20% of the connections in there. And that's liquid. Solid is going to be where most of the connections they can make are made. It'd be like all of you right now would be like a solid matrix for a substance. Okay? And that's because you're connected to the seats, which are then connected to the floor, right? And so you have a lot of anchor points. And so you can't move very easy, can you? You're kind of stuck in place. Now, that doesn't mean you can't move around at all. You can actually move around in your seats, right? And you are right now. And those would be equivalent to vibrations. I just vibrated that, didn't I? Okay? It's like you guys shifting your seats. All right, so this is a solid, and see how everything's bound tightly together. Anybody ever seen a snowflake magnified up? That hexagonal shaping that does for the snowflakes, that's actually the bonding pattern of water. So you've always known some chemistry, you just didn't realize it, did you? Okay. So when we look at a solid, it's going to have a definite shape and a definite volume. It's not going to flow. It's going to have very orderly particles. The particles in a liquid are going to be less orderly. They're going to be able to move freely. And so liquid is going to have a definite volume. It's not going to expand out to fill the container. In this case, the container would be the room, right? So for example, your guys' liquids here, they're not expanding out and going to fill the room, right? Yeah. So it expands out. It does not expand out. It has definite volume. However, it flows. and it takes the shape of whatever its container is. Okay? The particle's going to gas. They're not going to have any orderly arrangement. They're going to be very far apart from each other. They're essentially going to act almost not at all, very, very little. And they're going to move at high rates of speed. They're flying all over the place, bouncing everywhere. And they often collide with each other and with the walls of their container. This is actually what you're feeling when you feel gases. You're actually feeling the collisions. So for example, when I move my hand, the collisions on the back of my hand can't keep up. The collisions on my front of my hand increase. And so that's what I'm actually feeling. Okay? When I generate vacuum between my palms, right, by pushing the air out, that pressure I'm feeling is uneven collisions along the surface of my outer palms, no collisions inside my palms. Okay? And so my palms get pushed by the air particles that are colliding with them together, don't they? Okay? And that's vacuum. All right. And so that's actually what pressure ultimately is. It's uneven collisions on your surface. Okay? Okay, so gases, these have no definite shape or volume. They expand to fill the container in which it's placed. And so you don't really, it's kind of formless, right? Because it's not going to have a definite shape or volume. Typically, the container that a gas is in, unless you have very special setups for this, something airtight, is going to be the room or the entire world, right? Okay. So this is just a summary of these things we just talked about in a tabulated format, so you have them easy to hand. Okay. Note that one of the best ways to help you study things is there's a language to science, and so one of the easier ways to remember those terminology when you're learning a language at the beginning is flip cards. Okay, and so that's a hint. Might be a good thing to have if you're not remembering certain things. Accuracy and precision. So measuring with accuracy is going to mean that you're taking measurements close to the actual or true value. This is actually a very nebulous thing to actually really understand, because how do you know you're close to the true value? Or typically you use a book value to do it. But that does not mean that they have to be anything close to each other. So you can have measurements that are all over the place. As long as the average of them gives you the true value, they're very accurate, right? Okay. Precision, on the other hand, means that you're taking measurements that are very similar to value. They're going to repeat each other very closely. Okay? But being precise does not mean you are accurate. Okay? You can be very, very far off of the true value. An easy way to understand this is if I had a tape measure, but my tape measure had half of it ripped off, then I'd get very similar measurements every time I use it, right? But they'd all be wrong, wouldn't they? So I'd had very good precision, very poor accuracy, right? Okay. So in taking measurements, it's best to measure with both accuracy and precision. If you're very accurate but low precision, then you're going to have a large range of values that will all fit within your measurements. Okay? And this is where you start seeing that plus and minus, like 100 plus or minus 10, those sort of numbers, is that value could have very good accuracy, but has pretty miserable precision, right? Okay. All right. Now, this is typically accomplished by taking measurements several times, then you average their value. This is going to give you both increasing precision and increasing accuracy. Okay? It only gives you increasing accuracy, though, if you do not have a systematic error. Can anybody tell me what a systematic error would be? Remember my example with the tape measure? That's a systematic error, isn't it? Every measurement I take is going to be wrong because I'm missing part of the tape measure, right? So every single measurement is wrong, isn't it? Okay? And so if I go out and buy a new tape measure, I can remove that, can't I? Okay? By the way, has anybody used tape measures? Everybody's used them, right? Okay. Did you know that all tape measures have systematic errors? So anybody notice that that tip is adjustable? Has a screw there, and it can move around? Yeah, that's actually meant for you to measure against a standard, and you can tighten it down. Yeah. So better tape measures will actually be able to do that, and they'll come with some sort of standard for you to do. Because the tape measure is going to damage over time and loosen and move. So it's actually a correction factor. I know. Wow, tools have corrections. So let's talk a bit about units and dosing. So healthcare professionals use an SI or metric units. They have to be familiar with the U.S. customary system of measurement as well, so that if they get one device in one system of units, they can transfer it to a standard unit value that they would use in the hospital. Okay? Anybody think this happens on a regular basis? Oh, yeah. Oh, yeah. One of the biggest ones is a hospital during COVID couldn't get any of the syringes that they normally got and ended up getting different syringes that said cc versus milliliter on them. And so they had to do a whole training seminar for all their staff that, like, cc's are milliliters and this is how you do conversions. And, and it happens fairly regularly. Like manufacturers will just change over their devices and the markings on them because a lot of the manufacturer people are scientists and we're just used to conversions. And then they don't think about somebody might not be used to them. So it happens a lot more than you think. This right here is the property. This is the U.S. customary unit. This is the SI or metric equivalent. And that's the conversions right there. And so we have pounds versus kilograms. And then we have ounces as well. Here's quarts, liters, milliliters, fluid ounce. Note that ounces and fluid ounces are different things. Be careful about that. There's also a weight ounce. There's actually multiple weight ounces as well. So there's multiple fluid ounces, multiple weight ounces. This is the U.S. standard fluid ounce. Okay. Mile and inches and feet, of course, versus the kilometers, centimeters, and meters. Okay. Anybody know what a foot is based on? No? Okay, foot is based on a person's foot. It was one of the King Louis. Okay? Anybody know what a yard is based on? It's the stride of a beast of burden. So when you're behind the plow, you can count the number of strides taken. That's the number of yards. Okay? Anybody know what a meter is? That one was originally the width of oxen's shoulders. I know, right? These all have different unit bases now, though, that are repeatable throughout the universe. So let's talk a bit about reading lab reports. So if a patient results are given along with normal values, if the result is out of range, it would be highlighted. Values are going to be listed as greater than 1, but this makes the units on the numbers vary widely. And so most of the units are going to be metric for these. A deciliter is 1/10 of a liter. That's 100 milliliter. A millimole is a millimole. Mole is millimole. This is 1,000th of a mole. If a unit is used to convert the particles in matter, a similar unit will be used for the electrolytes. For example, we could have milliequivalents, which is small m equivalent, EQ. And so this is what's typically used in measurements for electrolytes. Okay? We'll actually cover these ones a little bit more when we get to the chapters about concentrations and moles, okay? So in the United States, body weight is usually measured in pounds. Pharmaceuticals, however, are usually dispensed in body weights that are in kilograms. A lot of hospitals will have done these conversions between pounds and kilograms for you. However, sometimes when we get new drug distributions, which happens quite often, what you would end up seeing is the guidance from the pharmaceutical company will be in kilograms. So you're supposed to deliver this many milligrams per kilogram of body weight. And so you would want to convert kilograms to pounds, right? this many milligrams per pound of body weight. Unless all your equipment's in kilograms, in which case keep it in kilograms, right? Yeah. Let's talk about calculating a dosage. So step 1 would be determining the units for the final answer. You'd want to determine what do I want to be in terms of units. Step 2 is determine the given information. What information have I been provided with? Step 3 is determine the conversion factors to cancel the units. And then step 4 is set up the equation with the given information and conversion factors so that all the units will cancel except for the final answering unit. So once all the units cancel, we can be assured that our answer is correct, assuming everything we put in was correct. Now, let's talk a bit about drop units because these are actually used quite a bit in like IV systems, and this is actually one of the common unit measurements in pharmaceuticals. Okay? And so IV delivery of medication is often measured in drops per milliliter. This is actually abbreviated GTT. GTT, by the way, is the Latin gutta, which means drops. And that's why that's GTT instead of just saying DR or DROP. No, honestly speaking, they're being a little bit silly by not probably just using drops. But there's kind of a reason for that. This is a very, very specific drop. Okay? With a very, very specific measurements for that instrument. If you were to use just a dropper, random one you picked up from somewhere, and try to measure out drops of a medication, this would not go over well. Okay? So the drop factor, this can be used to determine drip rates, which are then a prescribed volume of medicine that's required in a given time period. And so drop factors actually vary with the diameter of the IV tubing. So if you change out the IV tubing on an instrument and then try to set the dial for it, this will give them a completely different dose. Okay? Because the diameter of the IV tubing determines how fast the liquid flows, which then determines how fast the medication is given, doesn't it? Right? So if you ever see anybody messing around with the tubing for an instrument, and then somebody hasn't calibrated it afterwards, and there's little tags usually, if you look closely, that this has been calibrated on this date, like, go, hey, don't use that yet. Take that to the side and make sure it's been done, okay? It's actually one of the leading cause of people dying in hospitals is getting misdosed. So, and by the way, look for your own self. Okay, I'm going to take the last 5 minutes. Please get out your plickers. And we are going to do a bit of plicker. Oh, yes, I need to fix that. I'm sorry. Yeah. Dang it. Okay, we'll go for a couple more minutes and then we'll call it a day. Dang. All right. So let's talk about percents in health. So we have the percent active ingredient. So because of the high potency of many medicines, binders are often going to be used to increase the size of a pill. More often than not, these are things like cellulose powder. Does anybody know what cellulose powder is? It's basically ground up plant stock. Yeah. So like wood powder, essentially. Yeah. It's one of the most effective things. It's fiber. So you'll pass it. Why they do that is if I tried to measure out 1/100th of a drop, am I going to be able to measure that out successfully? I tried to move 1 grain out of the sand. Is that going to be something that I can measure successfully over and over and over? Here you go, 1 grain, 1 grain, 1 grain. It's going to be very difficult to do, right? And this is actually the biggest problem with fentanyl, in case you're wondering why everybody's poisoning themselves with fentanyl, is because people are buying the fentanyl from people that have not measured it out with binders and released it with binders. They're buying the pure substance. And then they're messing up the measurements and giving themselves multiple times the doses they should. Okay? And so they're killing themselves all the time because they don't know what the measurement should be. Right? In the pharmaceutical industry, we use binders to help that. And so what we do is we put 1,000 times the binder, and like 0.1% of it is the active ingredient that actually does the thing. Okay? That could be fentanyl, actually. Do you guys know fentanyl is an actual narcotic in use in the medical industry? Yeah. And so that makes it very safe then, because when you do a measurement, you can take multiple scoops to measure out the drug amount. It makes it much more accurate and much more precise in your measurements. Okay? Having said that, an interesting side note to this is, anybody ever seen those medicines that are used for the homeopathic effect? Medicines, I say, but not really. So the homeopathic effect is where you give somebody an irritant and it's supposed to make them less irritated by it. And those things are usually mixed up without taking this into account. And so many of those substances you buy from like Walmart that's a homeopathic medicine, those substances, you can't actually be sure if it has the active ingredient in it or not. In fact, usually about 80% of them do not have the active ingredient in them. They're actually just selling you like saline water. So, yeah. Okay, we'll pick up here next time. And then we'll move on to the next chapter. We'll also be doing a plicker. I'll bring the new plicker sheets and numbers. You all have a wonderful day. I'll see you Thursday.